Hello, IEEE ANTEM 2021. I am Amir Mansouri, and in this recording, I'm going to present our paper, which is Modeling Normalized Radar Cross-Section of Oil-Contaminated Sea Ice with Small Perturbation Method by Amir Mansouri, Dustin Sleifson, Durrell Desmond, and Gary Stern from the University of Manitoba, Department of Electrical and Computer Engineering, and Center for Earth Observation Science. This presentation includes 5 sections. I will start off by talking about background and motivation and the importance of this paper. Next, I'll talk about the taken approach for this research. I'll explain dielectric mixture modeling and scattering modeling techniques and results. Then I wrap up this presentation by talking about conclusions and future work. And finally, I'll demonstrate the references that I use for this paper. In summary, we present a study of surface scattering from oil-contaminated sea ice at C-band by the small perturbation model and simulating the normalized radar cross-section for both VV and HH polarizations. We utilized 5 dielectric mixture models to model clean and oil-contaminated sea ice with 2 types of oil products, crude oil and marine ship diesel, with 5% contamination by volume fraction. In the past decades, there has been a growing demand for the studies of the Arctic regions of our planet. Climate change, global warming, oil industry, shipping, and tourism in the Arctic region are the most important reasons for this attention to the Arctic. One of the ways of continuously monitoring the Arctic is using microwave remote sensing technologies. For instance, Canada's RadarSat constellation mission, which has 3 satellites, is one of the most recent launched remote sensing systems that observes the country daily. Recently, an increase in transportation in the Arctic has led researchers to consider the scenario of an oil spill in the region. In this scenario, the introduction of oil products into a sea ice environment would change the physical, thermodynamic, and dielectric properties of the sea ice. Remote sensing systems have been proven to be sensitive to the changes, and therefore have the potential for detecting and monitoring oil spills. This is extremely important for enacting a cleanup response and has significance for the government, industry, and Arctic communities. My aim in this paper was to improve the remote sensing techniques for better monitoring the region. By now, I introduced the importance of this research, and now I'm going to talk about the dielectric modeling methods and results of clean and oil-contaminated sea ice. First, I explain the procedure of clean sea ice modeling, and right after that, I talk about oil-contaminated sea ice modeling. To be able to model sea ice, we need to understand the structure of sea ice. Sea ice is a porous medium, and it's comprised of pure ice as a background with brine and air pockets as inclusions. For modeling, we used 5 different mixture models, including linear, refractive, cubic, Polder Van Santen Velour, and Tingavus plus A. In PVD and TBB modeling approaches in this study, the inclusions have been considered spherical. I need to mention that for the brine dielectric constant, we utilize expressions from reference 3. By modeling sea ice, what we actually do is that we represent the dielectric constant of the complex medium of sea ice with a single value that can be used in the normalized radar cross-section simulations, or in other words, in the scattering modeling. You can see a graphical representation of dielectric modeling in the figure in this slide. In order to model oil-contaminated sea ice, we consider the oil-contaminated sea ice as a mixture of clean sea ice and oil pockets. The modeling approach for oil-contaminated sea ice is like, first we modeled the clean sea ice background, where the brine pockets were considered inclusions in a pure ice background. Then we applied mixture approach, where sea ice was the background medium and the oil pockets were considered as inclusions. For the dielectric constant of crude oil and marine ship diesel, we use the data in our APSRC 2020 paper that is shown in reference slide as reference number 4. The modeled dielectric constants of clean and oil-contaminated sea ice at 5.5 GHz are shown in the table. As you see, the linear model has the highest real and imaginary parts and can be considered for the uppercase limit of modeling. The modeling results of refractive and cubic models are similar to one another. TVB model has the lowest real and imaginary parts amongst the five models. If we compare the modeling results of TVB and PVD with other models, we can see that the imaginary parts of these two modeling approaches are significantly lower. Now, I'm going to talk about the scattering modeling method and results for both clean and oil contaminated sea ice. For the purpose of a scattering modeling approach, we used a first order approximation of the small perturbation method, or SPM, for this study. The main idea of the SPM is to replace the surface roughness by surface currents on the mean surface. For equations and the theory of this model, you can check out reference number 1. In this paper, due to the low penetration depth of the incidence electromagnetic waves in C-band, specifically at 5.5 GHz in the sea ice medium, because of the high salinity of sea ice and drastic attenuation of the penetrating wave within the medium, volume scattering was not considered in our results. The NRCS simulation results of clean and marine ship diesel contaminated sea ice with the two different mixture models for VV and HH polarization for incidence angles between 20 to 65 are shown in these figures. As expected, by increasing the incidence angle, the backscattering for both the models decreases. There is good agreement between the simulation results of SPM and literature results of reference number 5. Figure 3 shows the ratio of VV and HH of clean to marine ship diesel contaminated sea ice, 5% contamination for the dielectric models. Results for crude oil contamination followed a similar trend. As the incidence angle increases, the ratio of HH backscattering of clean to marine ship diesel contaminated sea ice decreases, which means that the difference between clean and oil contaminated sea ice for HH polarization at lower incidence angles is higher. Conversely, increasing the incidence angle in VV polarization results in an increase in the difference between the backscattering of clean and oil contaminated sea ice. This means that VV polarization gives higher discrepancy between clean and contaminated sea ice at higher incidence angles. The highest discrepancy in VV polarization is related to the PVD model and is 0.18 dB, while HH polarization highest discrepancy is 0.13 dB. The discrepancy between clean and contaminated sea ice in PVD model is higher than that of refractive model for both HH and VV polarization. The results show that theoretically there is a difference in backscatter from clean and oil contaminated sea ice. However, the differences are extremely small for practical detection purposes. To conclude my presentation, I would say that adding oil decreases both real and imaginary parts of the electric constant of sea ice. TVB and linear models have the lowest and highest dielectric constants respectively. The differences between the NRCS results of clean and oil contaminated sea ice shows that there is potential for distinguishing these two types of sea ice, with VV showing greater potential than HH. However, in a practical sense, further investigation is needed. And for future work, the effect of oil migration through brine channels on salinity and surface roughness of contaminated sea ice and temperature effects on the electric properties can be considered. Finally, on behalf of our team, I would like to thank and acknowledge NSERC and the University of Manitoba for providing funding for this research, and our CIOS colleagues for their help and supports. Here you can see the references that I used for this presentation. Thank you again, and I'm happy to answer your questions.